All right, folks, here in section 2.6, we are going to look at and discuss something that's called continuity. So let's look quickly at an informal definition of continuity, something you might have seen in a prior college algebra class. So informally, we can say something is continuous, or an informal definition of continuity is the graph of a function is continuous at x equals a. That means that at x equals a, there are no interruptions in the graph. And when we say interruptions, we meant there's no hole in the graph, no breaks, like a jump, no vertical asymptotes, etc. Now, in the past, you may have heard someone say the function is continuous if you can draw the graph without lifting your pencil off of paper. Yeah, I've never liked that saying, by the way. I can draw a graph of something that is not continuous and not lift my pencil off the paper. But you may have heard that in the past, and so I wanted to acknowledge that. This informal definition was fine in an algebra class. But now that we're in calculus, it is not fine. We need to be a little bit more precise. So here's the real deal. This is the real definition of continuity. A function is continuous at a if the limit as x approaches a of f of x equals f of a. So let's look at what's really embedded in this definition, or what I call the moral of the definition. This definition really says that a function is continuous at a if all of the following are true. There are three conditions. It's almost like a checklist, if you will. So the first thing, f of a has to be defined. The second thing, the limit as x approaches a of f of x, well, it has to exist. And then the third thing is that the limit is equal to the function evaluated at a. So basically it's saying in number one, f of a has to be defined, so you have to get a value for f of a. 2 says the limit has to exist, so you have to get a value for the limit. And then number 3 says the value from 1 must equal the value from 2. So one more quick item. We're going to say a function is continuous on an open interval, CD, if it is continuous at each value in the interval. So we're going to do a couple of examples now. The first example is just going to be identifying where a function is not continuous. And then the second example is going to be finding intervals where a function is continuous. So let's look at the first example. Over here to the right is the graph of some function. Don't know what the function is, do not care. Just by looking at the graph, we are going to determine where the function is not continuous on the open interval 0, 5. And then at each point where we say it is not continuous, or at each point of discontinuity, we're going to state a reason why it is discontinuous. So you know the drill. Get this example written in your notes. Get that graph sketched in your notes. Because I'm going to head off to the chalkboard to do this example. And I'm also going to introduce some vocabulary terms while doing the example at the board. So here I go, off to the chalkboard. Hey folks, in this example, you're given the graph of that function. And we were asked, where is the function not continuous on the open interval 0, 5? And then at each point where it's not continuous, or at each point of discontinuity, state a reason why it is discontinuous. All right, so I'm looking at the open interval 0, 5. And the first value of x I see where it is discontinuous is x equals 2. So where is it not continuous? I'm going to say the first value I see is x equals 2. Now why is it not continuous there? It has to violate one of those three conditions, that checklist I just gave you. Quite simply, It's not continuous at x equals 2 because the limit as x approaches 2 does not exist. I'm going to give you one more little vocabulary word for this as well. That type of discontinuity is said to be non-removable. Now, non-removable means I don't have the ability to redefine the function and make it continuous there. And it's because the limit does not exist. Next, moving on. It's not continuous at x equals 3. So let me write that down. It's not continuous at x equals 3. Why? Why is it not continuous at x equals 3? Now, it's not enough to say, well, there's a vertical asymptote there, because there is a vertical asymptote, but the reason why there's a vertical asymptote is because f of 3 is not defined. And that's one of the 3 items on our checklist. It's number 1, actually. So it's not continuous at x equals 3. The reason why is because f of 3 is undefined. Okay, this type of discontinuity is also said to be non-removable. I can't redefine the function and remove that discontinuity because the function is not defined there. I don't have the power to do that. Here's one more vocabulary word that I'm thinking ahead to Calc 2 right now. That type of discontinuity is said to be an infinite discontinuity, but we'll worry about that in Calc 2. All right. Let's see. Anywhere else in the open interval 0 to 5 where it is not continuous, where it is discontinuous? Boom. X equals 4. At x equals 4, it is discontinuous. Now let's see why. The function is defined at 4. In fact, f of 4 is equal to 3. The limit exists. The limit as x approaches 4 of f of x means we approach 4 from the left side of 4 and we approach 4 from the right side of 4. It looks like that limit is 5. So when you look at your checklist, those 3 items, it satisfies number 1, it satisfies number 2, but it doesn't satisfy number 3. Remember, number 3 says that the limit would equal the functional value. So why is it not continuous? Why is x equals 4 not continuous? Why is it discontinuous? These aren't equal. So in short, we would say the limit as x approaches 4 of f of x does not equal the f of 4. That is why it is discontinuous. And by the way, this type of discontinuity is said to be, now this one is said to be removable. And the key is the function value was defined, the limit did exist. So I could remove the discontinuity by redefining the function, and instead of having f of 4 equal 3, I would make f of 4 equal 5. So that filled in circle would just move in, it'd move right up to here. So I could remove that discontinuity. All right, folks, let's head back to the slides and see what is next. All right, folks, in that example we just looked at on the chalkboard, we found 3 values of x where the function was not continuous, and we were able to introduce some vocabulary terms as to if it was a non-removable discontinuity. And if it were non-removable, I think I introduced also something called an infinite discontinuity. And if it were a removable discontinuity and what that looks like and what that means. So now in this example, we're going to determine the x values where the function is discontinuous. So we're going to determine the values of x where the function is not continuous. And here are 4 of them. So, get this written down, get it in your notes, because I'm going to head off to the chalkboard and work through each one of these. All right, in this example, we're asked to determine the x values where the function is discontinuous. Now, this is going to be matched up very tightly, almost exactly with finding the domain of the function. So look at the function in part A. It's 1 over x squared plus 1. Are there any values of x, any real number values of x, that would make that denominator 0? Of course not. The answer to that is no. The denominator will always just be a positive number, but there's no value of x that makes the denominator 0. That means we can put anything we want into the function for x. That means the domain is all real numbers. So x values where it's discontinuous, there are none. So determine x values where it's discontinuous, there are none. This function is continuous everywhere. All right, so now part B. What about the function x over x squared minus 1? Well, think of what the domain is. You would kick out of the domain any numbers that would make the denominator 0. Well, what makes the denominator 0? -1 and +1. The function is not defined at -1. Therefore, it's not continuous at -1. The function is not defined at 1. Therefore, it's not continuous at 1. So it matches up with the domain. So the x values where this function is not continuous, where it's discontinuous at x equals -1 and at x equals 1. Okay, part C and part D, here's what I'd like you to do. Since we've done a couple and I've told you how it matches up tightly with the domain, I would like you to pause the video and I would like you to do part C and part D right now. And once you've done part C and part D, restart the video and I'll be here at the board working through them. So pause the video, do part C and part D. All right, part C. The function is cosine x. It's a trig function, cosine x. We know the domain of cosine is it's all real numbers. You can put anything you want in for x. So that means this function is continuous everywhere. So just like part A, where is it discontinuous? There are no values of x where it's discontinuous. It is continuous everywhere. Part D, function is x minus 3 over x squared minus 9. Are there values of x that would make the denominator 0? Sure there are. -3 and +3. The function is undefined at -3, so it's not continuous there. The function is undefined at 3, so it's not continuous there. Those are the two values of x that would make the denominator 0. So just like in part B, this function is discontinuous at x equals -3 and at x equals 3. All right, folks, hopefully you got those two. Let's head back to the slides and see what the next topic is. All right, folks, we just saw it's not too bad to determine x values where a function is discontinuous. It kind of matched up nicely with, basically matched up nicely with being able to determine the domain of a function. So next is another example. We're going to use the graph to the right to answer the following questions. So there's the graph of some function over here to the right. Don't know what the function is, don't care. Notice that there's a filled in circle at -1, 0, and there's an open circle at -1, 2 on the graph of the function. So part A, we're going to determine the limit as x approaches -1 from the right side of -1 of this function. And in part B, we're going to determine the limit as x approaches -1 from the left side of -1 of the function. And when we approach -1 from the right side, I see that the limit is 0. We approach -1 from the right side of -1. Those y values are getting closer and closer to 0. As we approach -1 from the left side of -1, so we're coming from the left side, it looks like those y values are getting closer and closer to 2. So I think in part B, the limit is 2. Part C, what is the limit as x approaches -1 of f of x? So what is the limit? Well, since the right-hand limit is 0, the left-hand limit is 2, we know that means the limit does not exist. And then in part D, is the function continuous at x equals -1? If it's not continuous, if it's discontinuous, is it a removable discontinuity? Well, we know it's not continuous at x equals -1. We know the answer to the first question here is no, because the limit does not exist. Is it removable? There is no way I can redefine the function to remove that discontinuity. So the answer there is no. So I just wanted to do one more example. And let's see what we're going to look at next. We're going to consider our old buddy, the function f of x equals square root x. And there's the graph of square root x. Now notice I'm just looking at the graph of square root x on the interval, the closed interval, 0 to 9. And I have a question here. Is the function continuous on the closed interval 0, 9? Well, based upon what we currently know about continuity, we only know about continuity on open intervals. Technically speaking, it is not continuous on the closed interval 0, 9. Because technically speaking, the limit as x approaches 0 of square root x does not exist, because you can't approach 0 from the left side of 0. Now we want to fix this. We do want to say that the function f of x equals square root x is continuous on the interval, the closed interval 0, 9. We want that to be true. So here's how we fix this. We have a new definition coming up, so we can fix it and say that square root x is continuous on the closed interval 0, 9. So here's the definition. A function f, we're going to say it's continuous on the closed interval ab if it is continuous on the open interval ab, and the limit as x approaches a from the right side of a of f of x equals f of a, and the limit as x approaches b from the left side of b of f of x equals b. The limit as x approaches a from the right side of a of f of x equals f of a. Some people will say that means f is continuous from the right of a, whereas the limit as x approaches b from the left side of b of f of x equals f of b, people will tend to say that means the function is continuous from the left of b. So think back to the square root of x on the closed interval 0, 9. On the closed interval 0, 9, square root of x is definitely continuous on the open interval 0, 9. And if you do the limit as x approaches 0 from the right side of 0, you're going to get 0, and the f of 0 is 0. So that satisfies our first condition here. And if you look at the limit as x approaches 9, from the left side of 9, of square root x, you're going to get 3, which is equal to the f of 9. That satisfies the second condition here. So that's how we can now say, yes, square root x is continuous on the closed interval 0, 9. But let's check out an example here. Let's determine intervals where this function is continuous. And, so you know the drill, write this in your notes. I'm going to head off to the chalkboard to do it. And again, we're going to see it's closely related to just determining the domain of a function. So get it in your notes because I'm heading off to the chalkboard to work through this. All right, now we're talking about intervals of continuity. So in this example, determine the intervals where the function is continuous. And the function we were given was the square root of x to the fourth minus 1. So again, this still matches up with our concept of domain. So I'm just going to find the domain of this function. So it's a square root. That's an even indexed root. Remember, what's under the square root symbol can't be a negative number. 0 is not in the domain of this function. Because if 0 goes in for x, we would end up with a negative number under the square root. And we can't do that in the real number system. So look at what's under the radical, x to the fourth minus 1. It is not allowed to be negative. Well, if it's not allowed to be negative, that means it is allowed to be positive. It also is allowed to be 0. So what's under the square root must be greater than or equal to 0. I'm going to solve this inequality. That'll tell me the domain, and it will tell me the intervals where the function is continuous. So the way to solve this is, we start by factoring. This is the difference of two squares. It factors to x squared minus 1 times x squared plus 1. Well, and then x squared minus 1 is the difference of two squares. It factors to x plus 1 times x minus 1. So now I've completely factored x to the fourth minus 1. And then this is the key on, I'm going to end up making what is called a sign diagram. And this is the key in how to make the sign diagram. Because there are a lot of combinations for these three factors in order for them to be greater than or equal to 0. This could be negative and this could be negative, and that product would be greater than 0. This could be positive and this could be positive. So a sign diagram will quickly condense my work so I don't have to look at a bunch of cases. So look at your factors. When are each of those factors equal to 0? Well, x plus 1 is equal to 0 at negative 1. X minus 1 is equal to 0 at positive 1. X squared plus 1, well, that's never equal to 0, which is kind of cool. So let me come over here and make a sign diagram. Maybe you've seen something like this back in a college algebra class, which would be kind of cool. I put these values of x on a number line. So there's negative 1 and 1. And then what I do for my bookkeeping is I list the factors that gave those zeros right here. So x plus 1 gave us this, and x minus 1 gave us this. Notice I don't need to put x squared plus 1 anywhere in there because x squared plus 1 is never equal to 0. In fact, x squared plus 1 is always positive. But back to the sign diagram. I then tend to make some vertical dashed lines. This is all like bookkeeping. And then I do the following. X plus 1 was 0 at negative 1. And x minus 1 was 0 at positive 1. Okay, these numbers split the real number line into 3 subintervals. Just pick a number that you know is in the interval from negative infinity to negative 1, like negative 2. If you put negative 2 in here for x, you would get a negative number. That means x plus 1 is negative for any value of x you can think of on the interval negative infinity to negative 1. Pick a number that you know is in the interval negative 1 to 0. Or I'm sorry, negative 1 to 1. Yeah, I would pick 0. Put that in here for x. X plus 1 would be positive. So for any number you pick in this interval, negative 1 to 1, x plus 1 would be a positive number. And then if you pick any number out here, you would see x plus 1 is a positive number. Repeat that for x minus 1. So if negative 2, which is in this interval, went in here for x, out would come a negative number. So no matter what number you pick in this interval, x minus 1 will be negative. No matter what number you pick in this interval and put in for x, x minus 1 would be negative. And no matter what number you pick in this interval and put in for x, x minus 1 would be positive. Since I want to know when I'm looking at a product here, let's multiply them together. On the interval negative infinity to negative 1, x plus 1 is negative, x minus 1 is negative. A negative times a negative is positive. On this interval, the product would be negative. And out on this interval, the product would be positive. This line that I've written in red answers the question, because I've already said x squared plus 1 is a positive number. It's always positive. So when is the product of these 3 factors greater than or equal to 0? Well, on the interval negative infinity to negative 1, include the negative 1, because that's where it would be equal to 0. Union with, include the 1 to infinity, because at 1, the product would be equal to 0. So where's the function continuous? Right there, folks. So let's head back to the slides, and I think we're going to revisit another familiar topic from algebra. All right, I've been discussing a lot about continuity, intervals of continuity, how it matches up with just simply being, like the domain of the function. So let's look at a few continuity facts that I think will be helpful for you to remember. The first one deals with polynomial functions. Polynomial functions are the friendliest functions we could possibly deal with. Polynomial functions are continuous everywhere. That's pretty nice to know. Rational functions. Remember, a rational function is a polynomial over a polynomial. Well, rational functions are continuous for all values of x, provided the denominator does not equal 0 for a value of x. Or in other words, a rational function is continuous for all x in the domain of the rational function. Let's talk briefly about trig functions. Trigonometric functions are continuous for all values of x in the domain of the said trig function. That's nice to know. So a few friendly continuity facts for you to remember. Now our final topic in this section, I'm pretty sure it's one that you've seen in college algebra. You may not have been told this in college algebra, but I'm telling you now. It is an example of what in mathematics we call an existence theorem. Now, an existence theorem is nothing more than a theorem that tells us when something exists. It doesn't tell us how to find it. It just tells us, hey, this exists. So let's look at what this existence theorem is. And what we're going to do is head off to the chalkboard to motivate this theorem. It's a theorem you would have seen in college algebra, but I'm going to head to the chalkboard to motivate it. All right, folks, I said we were going to come here to the board to motivate this next topic. So here we are. Here's a graph. And, I would generally ask a lot of questions about this graph. So, here's a question I would ask. Look at the graph of that function. I don't know what the function is. I don't care what it is. Is the function continuous on the closed interval AB? And you would tell me yes. So I just kind of make that a bullet item here. The function is continuous on the closed interval AB. Okay, so I don't know what the function is. Here's A, here's B. I know this y coordinate is f of A. I know this y coordinate is f of B. Oh, doesn't it look like I have arbitrarily and in red located some number k that is between f of A and f of B? Yeah, it looks like that, so I'll just make that note here. K is some number between f of A and f of B. Well, since the function is continuous on the closed interval AB, and k is between f of A and f of B, it seems that means there is some number that I'll call C. It looks like that C is between A and B, and it looks like f of C would equal k. So I'll make that as a bullet here. F of C is equal to k, and C is between A and B. In other words, C is in the open interval AB. Okay, all of those observations come together into an existence theorem that is called the intermediate value theorem. I'm sure you've seen this in a college algebra class, the intermediate value theorem. But we're going to head back to the slides and we're going to formally write down the intermediate value theorem. It is an existence theorem. It's just telling us where something exists. And the key things for the intermediate value theorem will be the function has to be continuous on the closed interval AB. So let's head back to the slides and see officially what the intermediate value theorem is. All right, as we saw on the chalkboard, we motivated this theorem. This theorem that we motivated and, we had a nice picture for is called the intermediate value theorem. And the intermediate value theorem, in all of its glory, one more time, it says if your function is continuous on closed interval AB and k is any number between f of A and f of B, then there exists at least one number C that's in the open interval AB such that f of C is equal to k. And one of the most useful things about the intermediate value theorem comes out in this example. We're going to use the intermediate value theorem to show that the function f of x equals x cubed minus 13x plus 12 has a 0 in the closed interval -5, -3. So write this down. I'm heading off to the chalkboard to work through it. All right, this example, we're going to use the intermediate value theorem to show that the function f of x equals x cubed minus 13x plus 12 has a 0 in the closed interval -5, -3. So the first thing I have to verify is that my function is continuous on the closed interval. So I'd ask the question, is that function, x cubed minus 13x plus 12, is it continuous on the closed interval -5, -3? The answer is yes. It is continuous on that closed interval. And there's a good reason why. The function is a polynomial function. And we know polynomial functions are continuous everywhere. So it's definitely continuous on that closed interval. So now to use the power of the intermediate value theorem, it's an existence theorem. It's just going to show us, yep, there's a 0 in that interval. You need to evaluate the function at -5. So that means you got to put -5 in for the x's. And if you evaluate the function at -5, when I do that and I use my calculator, I get -48. Then you evaluate the function at -3. So I put -3 in for the x's, and what comes out is 24. All right, now folks, 0 is somewhere in there between -48 and 24. So 0 is between -48 and 24. So your intermediate value theorem says, since 0 is in here somewhere, there exists some number that I'll call C in the interval -5, -3, such that f of c is equal to 0. I mean, think about what this means graphically. I'm not going to draw the graph of this function. I'm just going to point out what we found. So let's see. So there's -5. We said f of -5 was -48. Okay, so I'm just going to put that right here. So it's on my board somewhere. That's a point that's on the graph of the function. We said f of -3 is 24. So I'll just arbitrarily put it about right there. That point is on the graph of the function. Because the function is continuous, when you connect these 2 points with the graph of this function, you have to cross the x-axis somewhere. That's the value of c, where f of c is 0. That's the beauty of continuity. So, I'm sure that's an old topic. I'm sure you saw in college algebra, but now we're looking at it in calculus as an example of an existence theorem. We're going to have a few existence theorems throughout calculus. But that's it. That's it for section 2.6 in continuity. So at this time, you're good to go. So you can now do the exercises in 2.6. So please do those exercises in section 2.6. And thanks for watching.